Welcome to Spring LIB.
This is the answer to Chapter 12, problem number 55 from the Smith Organic Chemistry textbook. And in this problem, we are told that oxamine and myrcene, two hydrocarbons isolated from alfalfa, we're told that they both have the molecular formula C10H16. They both give 2,6-dimethyl-octane when treated with hydrogen gas and palladium. And then we're told about the ozonalysis products of each of them. And so we are asked to identify the structures of oxamine and myrcene. This is a good problem because this gives us lots of pieces of information, certainly enough information to determine these two structures. And we just need to know basically what to do with the information that we've been given. The very first thing to do, I think, when we're given a formula and asked to find a structure, the very first thing to do is always to determine the hydrogen deficiency index, the HDI. And so that's going to tell us how many double bonds or rings there are in these molecules. And we can see that there's not going to be any rings, right? Because when the molecules are hydrogenated, they both give 2,6-dimethyl-octane. And so we know it's going to be a matter of how many double bonds are in these molecules. And so that's what the HDI is going to tell us. And so remember, HDI is for a molecule where it's just carbons and hydrogens, it's going to be 2 times the number of carbons plus 2 minus the number of hydrogens. And then all of that is going to be over 2. And so here we have 22 minus 16 is going to be 6 over 2 is going to be 3. So each of these molecules is going to have 3 double bonds in it. Okay. So that's that's helpful. Now we just need to determine where these 3 double bonds are going to be. And so we can start with oxamine. And so for oxamine, we're given the products of an ozonalysis of oxamine. And so what that tells us is exactly where our double bonds are. So we just need to write these ozonalysis products out and then line them up so that carbonyl groups are facing one another. And then we just need to link all of that up. And so I will demonstrate what I mean. So let's see. So we have acetone. And because because we know that we have something based on the structure of 2,6-dimethyl-octane, I think acetone is a good piece to start with because it's going to be the left section of our molecule here. So here's our acetone. Okay, and so let's see what else we have. We have a formaldehyde. We have CH2, so a 3-carbon dialdehyde. Okay, and then we have a ketone and an aldehyde together. Okay, so I'm going to say that our 3-carbon dialdehyde is the next piece. Okay. Okay, I see. So then we have another 3-carbon piece that is an aldehyde. ketone here. Okay. And then our formaldehyde. All right. And so we have these pieces, and what we can actually do, and why I drew them out this way, is we can just link carbon to carbon, carbonyl carbon to carbonyl carbon. And remember that instead of carbonyls, we're just going to have double bonds between those two carbons. And so when we draw this product out, one, two, three, four, five, six, seven, eight. Okay, good. So this is correct here. So this is the way that these pieces link together. This molecule has 3 double bonds. And when hydrogenated, it would give us 2,6-dimethyl octane. So this is the structure of the oximene. And again, the way that we really determine that is to just draw the pieces that were given out so that we can link them together in such a way that they're going to give us that 2,6-dimethyl octane backbone, and then just sort of see where our double bonds fall. And so I'm going to do exactly the same thing for the myrcene. Okay, so let's see the pieces that were given here. So again, we're given an acetone. So that's definitely going to be this leftmost piece again. Let's see, we have 2 equivalents of formaldehyde this time. Okay. All right, good. So this is a much easier one then. 1, 2, 3, 4, 5. So we have a 5-carbon linker section in the middle here. So aldehyde, 2, 3, 4, 5. Oh, 1, 2, 3, 4, 5. Okay, I see. So a ketone here and an aldehyde. Oops. An aldehyde right here. Okay. And then 2 equivalents of formaldehyde. So here's going to be 1 formaldehyde, and then put the second one. Do it like this. Okay, and so there's our second formaldehyde. And then we can do exactly what we did for the oximene and just link carbonyl carbon to carbonyl carbon. And so when we do that, we see that again, we're going to have something based on this 2,6-dimethyl octane backbone. But this time, what we have is our double bond here. And that's really the only change. The other 2 double bonds are in the same place as they were for the oximene. But that double bond is there now. And so that became pretty apparent when I saw that we had a second equivalent of formaldehyde. And so that's the way to approach this problem. Start by calculating the hydrogen deficiency index and determining what that's telling you about the molecule. And then just look at the pieces that you're given and try to line them up in such a way that they fit the 2,6-dimethyl octane backbone. And then just link carbonyl groups to tell you where your double bonds are. And that's the answer to chapter 12, problem number 55.